Okay, so picking up where we left off yesterday. Tonight, by the way, is the last night to get into Worst Fest for free. So they extended it to Wednesday. Anyway, good to know if you want to go. Save $15 to get in. Yeah, no, free for everybody. Yeah. It used to be just Monday and Tuesday. Now it's Monday, Tuesday, Wednesday. So good to know because it's $15 otherwise. Okay, so we are now looking for a way to find extrema. And, of course, when I say extrema, that means absolute, max, absolute, mins on a closed interval, okay? On a closed interval. There's going to be a way to justify on a open interval later on, okay? So closed interval means we have endpoints to find the extrema of a continuous function, okay? So what theorem was it that says if we had a continuous function on a closed interval, that we would actually have a guarantee of both a max and min? EVT, right? Extreme value theorem. So if we have a function that's continuous on the closed interval, we need to, number one, identify the endpoints. Okay, that's pretty easy. They're going to be pretty much given to you, right? Once we have the endpoints, then we need to identify any critical values that are in the interior of that closed interval, right? Now, you got to be careful because you need to verify, first of all, that they're in the domain. If they're not in the domain of the function, they're not really critical values. But then you also need to make sure that they are inside the interval. You may have a critical value that's outside a specified interval, okay? And then once you target all those critical values that are in the interval, you then play the game, essentially, of finding the biggest and smallest y value just by plugging those x values into the original function. So the only thing we're really using calculus for is to find the critical values. Other than that, we're just plugging into a function and finding the y values. So we'll be finding the y values at the endpoints and the y values at any critical values on the interior. And once you have all of those computed, the largest y value is going to be the max, and of course the smallest value is going to be the min. And then we answer the question in a complete sentence. Right now, we're pretty confident, very confident, 100% confident that it's going to either be at one of those endpoints or one of those critical values because of what we've been doing. Okay, that was actually a theorem that said local extrema can only occur at a critical value on the open interval. So relative extrema are possible absolute extrema. So you could think about it as like playing a game. Wouldn't it be awesome if there were a game show called Extrema, right? Kind of like Jeopardy, right? Extrema. And to be a contestant on the show, you have to, A, either be an endpoint, or B, be a critical value in the interval, right? And you can kind of see the contestants are kind of in there behind their buzzers, and the announcer, who's going to be the biggest Y value? Who will be crowned the global maximum at the end of today's show? Will it be contestant A, the ginger on the left? Will it be contestant B, the creepy old guy on the end? Okay, so we got the left endpoint, the ginger, and we got the creepy old guy on the right endpoint. Or will it be contestant C, the fist-pumping critical value on the interior? Who will it be? We'll find out right after this. Okay, yeah, I'd watch that. I'd watch that. Okay, so yeah, in this little picture here of the game, we're going to say that the redhead woman on the left is the left endpoint, and the creepy slouching guy on the right is the right endpoint. And the girl in the middle, the fist-pumping girl, is there's only one critical value on the interior. There could be several, right? If we let their scores represent their y values, they're way up there. By the EVT, if this was a continuous function, one of those would be guaranteed to be the max, and one of those would be guaranteed to be the min. So who would walk away with today's absolute maximum prize? The right endpoint guy, right? The creepy guy on the end has the biggest value, 4220. So he is the winner of the absolute maximum prize today. And who is the biggest loser? The absolute minimum, who's also a winner? Fist pump, right? Critical value. She's the smallest one. So those two people out of three, they win the award. So notice one of them was at the endpoint, one of them was at a critical value. And what does the redhead win? At the end of the day, everyone who plays the game walks away not empty-handed. They have a what? What did you give them? A soul? Oh, you could. I usually give them a broken toaster. right? Yeah, for participating, right? Congratulations, here's a broken toaster, right? And they're like, thanks, just for participating. Okay, so let's go ahead and play this awesome game. Example 7. Determine, first of all, if the EVT applies. If it does, then find the values guaranteed by the theorem for that function f on that closed interval from -1 to 2. Okay, how do we know if the EVT applies or not? What are we looking for? Continuity on a closed interval. That's all we need. We have the function f of x. It's a polynomial. We have a closed interval from -1 to 2. Where are polynomials continuous? Everywhere, right? Even in France. So we have a closed interval from -1 to 2. The EVT applies. So all we have to say is EVT applies because f of x is continuous on the closed interval from -1 to 2. So just like when we had the IVT, you can make kind of a blanket statement like, I love blankets. That's not what I mean by a blanket statement. You can make a blanket statement like f of x is continuous for all real numbers. And that certainly would include the closed interval from -1 to 2. But you don't want to do it that way. You want to speak specifically to the theorem, okay? So yes, it is continuous for all real numbers, but more specifically in this case, it's continuous on that given closed interval, okay? So now I know there's going to be both a max and a min, and it can occur at either an endpoint or a critical value. So as we gather our contestants for the show, Extrema, do we already have a contestant team? Do we have team endpoint already in the house, in the green room? Yes, we have x equals -1 and x equals 2. So team endpoint is in the house. We'll put them in the green room where they can eat stale Cheetos until it's time to come out. Stale Cheetos, I don't know. Goes with broken toaster, I guess. Now we need to find out, we need to go rouse up our other contestants. So it's kind of like on The Price is Right where you have to go into the crowd and look for them, right? So those are going to be our critical values. So what do we do for that? We need the derivative. So f prime of x is 12x cubed minus 36x squared. Now remember, we always check two things. Where is it undefined and where is it equal to 0? We don't have to write it down. We just want to consider it. Is f prime ever undefined? No, it's a polynomial. So it's always defined. So the only things we're looking for now are where it's equal to 0. So let's go ahead and do that. If you're only going to use this equation once, you don't have to go down on a fork and rewrite it. You could just do it right there. Set it equal to 0. Now that it's equal to 0, first of all, you would get a check for that. We'll factor it. We can pull out a 12x squared, and that leaves us an x minus 3 equals 0. And then from there, you could probably just rattle off the roots, right? What are they? X equals 0 and x equals 3. Now, before you let them play the game, ask yourself two questions. Are those values in the domain of our original function f? Yes. Okay. That would be equivalent for the real game show, like, are these people alive? We need them to be alive to play the game. They need to exist to play the game. They need to be alive. Yeah, they're alive. They exist. But we also need them to live in a region. It's like people that run for office. You have to live, if you're representing a district, you have to live typically within that district that you're trying to run to represent. That's what we're doing here. They have to live in the interval. Our interval is from -1 to 2. Are both of those dudes in the interval? No. So sorry, x equals 3. You are a critical value of the function indeed, but we haven't come to your hometown yet. We'll be there someday, maybe. So x equals 0 is the only one. So are they in the interval that's specified? Okay, and so we only have one of the two that, met the profile to play the game. So it kind of seems like the teams are unbalanced now, right? Team endpoint has 2 players. Team critical value only has 1. It doesn't matter. All right, so now that we have all our contestants, let's play Extrema. Here's how we play the game. F of -1, F of 0, and f of 2. The order in which you compute these doesn't matter, but I always like to list them in increasing order. So I did the left endpoint first, then the critical value 0 in the middle, and then the right endpoint on the bottom at the end. Okay? So let's play that game. Team endpoint, why don't you go first? All right? -1, you take it away. How do we do that? How do we find f of -1? Yeah, we're doing algebra, people. We're just plugging and chugging. So if you plug in a -1, you get 3 plus 12, which is 15. All right, now let's give -1 a round of applause. He had to go first. That's not easy to do. He established kind of the benchmark of 15. Well done. Well played. Well played. Okay? All right, let's alternate. Team critical value, you go next. Okay, plug in a 0, what do you get? 0 minus 0 is 0. Oh, way to go. I see what you did there, team critical value. You went low. You just stole the absolute minimum prize from team endpoint. Well done. Well done. Well done. Okay? Now it's f of 2's turn. If team endpoint wants to go with the clean sweep here and win both the max and min, then 2 should go low or high. He should shoot for low, right? He should shoot for something less than 0, and then he'll be the min and his teammate will be the max, and we'll exclude team critical value, right? So here we go. 2, you take it away. 2 to the 4th, 16. 16 times 3, 48. I'm going to write that down, 48. Minus, plug in a 2. 2 cubed is 8. 8 minus 12, or 8 times 12, sorry, 96. And that equals, we'll find out right after this commercial break. Oh, I can see the drama. All right, welcome back to the studio. 48 minus 96 is -48. Did they do it, folks? Did they do it? Dramatic finish. Team endpoint took both the max and min prize. Good. So, by the EVT, comma, F has a min, and of course that means absolute global, of y equals what? -48, and we'll go ahead and say at x equals 2, the right endpoint, and a max of y equals 15 at x equals -1. So team endpoint went with the clean sweep there. Of course, it has nothing to do with these x values trying to go high or trying to go low, right? That was just for dramatic effect. They're at the mercy of the function. You just plug them in, okay? And when you do that, you'll be staring at a max, you'll be staring at a min by the EVT. So that's called the closed interval argument. We calculate the y values at the endpoints and at every critical value on the interior, and then indubitably by the EVT, we're going to have both the max and min. All right, fun game, right? Fun game. Let's go ahead and try and play the game again. Let's try and squeeze another one in here before lunch. Determine if the EVT applies. If so, finds the extrema on the closed interval from -8 to 1. Is this function continuous on the closed interval from -8 to 1? How can we tell? Well, remember the domain is going to be interrupted. Unless it's a piecewise function, the domain is going to be interrupted by discontinuities. Discontinuities are of the vertical asymptote whole jump variety, which means we would get division by 0 or something like that. Do we ever get division by 0 here? No, we don't have any x's in the denominator. And the radical is a cube root. So we can have negatives under there if we wanted, but oh, by the way, it's squared, we don't. So guess what the domain is? All real numbers. So guess where this function is continuous? All real numbers. Yeah, these power functions are continuous over their domain. So you could just say EVT applies because f is continuous on the closed interval from -8 to 1. You don't have to prove it. You just have to say it. And you definitely want to say the right thing. So you need to check it and make sure that it is. Okay. So we already have, again, team endpoint ready to go, -8 and 1. We need to find the critical values. Now, before we take the derivative, are we on any kind of alert? Cuss blurt, cuss blurt, cuss blurt. Aruga, aruga. Why? Yeah, the exponent is between 0 and 1. So that, when we take the derivative, is going to become negative, which is going to force it to the denominator, which means now when x equals what? We're going to have a discontinuity on the derivative, or a place where the derivative doesn't exist. What value is that? What's the root of that? 0. So I know that x equals 0, there's going to be a critical value, for sure. Now, it'll come out in the calculations, but we just want to be mindful of that to begin with. Would that actually be a relevant critical value for our interval? 0? Yeah, it would be. All right. So let's go ahead and take the derivative. F prime of x is 2x becomes 2, and then minus, when we multiply, we get 2x to the negative 1/3. Okay, so right now, you want to be careful. You don't want to set it equal to 0. If you're going to have a denominator, and we do, that's the same as 2 over the cube root of x, then you're going to want to get a common denominator to combine your terms. Now, you could do it by factoring out the least powers, if you wanted, on the line above, or in this case, you could just write it like that and get a common denominator by multiplying the other one by what you need, which would be the cube root of x over the cube root of x. I'll just show it like that. And so that equals then the 2 cube root of x minus 2 all over the cube root of x. And now I'm going to do one more thing. In the numerator, I notice I could factor out a 2. So that's 2 times the quantity cube root of x minus 1 all over the cube root of x. This, again, is what I called the full-fledged factored version, the full-fledged factored version of f prime. That's the one that we want because it's easy to use. Okay, so now we're going to use it twice, aren't we? Because it's a quotient. So I'm not going to just set it equal to 0. I'll say f prime equals dne when the denominator cube root of x equals 0. So if I cube both sides, I get x equals 0. That's going to be your vertical tangent. All right, so that's going to be, like we said yesterday, either a local max, local min, or it's going to be one of these vertical going through it, decreasing or increasing through it. All right, so 0 is in the domain of the function, right? The original function, 0 is in the domain of f. So he's in the domain. Is he in the interval? Yes. So those are really the only two qualifications. Like, he shows up to the studio, can I play? Are you alive? Yep. Do you live in this region? Yep. Come on in. All right. So now we do the other fork. We come over here, and we say f prime equals 0 now when the numerator is 0. So that's 2 parentheses, cube root of x minus 1 equals 0. And you can kind of solve this in as many or as few steps as you need. Divide by 2 and add 1, and you get the cube root of x equals 1. Cube both sides, and you get x equals 1. Okay? Now, is 1 in the domain? Yeah, the domain was all real numbers. Is x equals 1 in the interval? Oh, he is. He's already playing, right? He's the right endpoint. And he's a critical value. So he isn't in the open interval, but you could say he's in the closed interval. That's fine. He's going to play, but he's going to be playing for both teams, isn't he? He's an endpoint and a critical value. He's like full-time quarterback, if you've ever played that on the playground, right? Didn't have enough guys, or you had one guy that was a really good quarterback. Okay? I like to be full-time tackler. All right, so let's play Extrema. We got f of -8. We have one critical value on the interior. That was 0. So f of 0. And then f of 1 and f of 1. Do we need to compute it twice? Nah. All right, here we go. Now, when you're evaluating it, notice the version that I wrote up above here might be a little bit easier to use, right? So if I plug in a -8 there, I'm going to get -16 minus. Now here, instead of squaring -8, Let's take the cube root first. What's the cube root of negative 8? Negative 2, right? And then negative 2 squared, positive 4. Okay? Try to go small before you go big. And then positive 4 times 3 is 12. So I end up with a negative 28 there. Okay, so plug in carefully. Write it as a radical if you need to. Now what do you get when you plug in a 0? 0 minus 0 is 0. All right, so f of 0, the critical value, just stole the absolute max from negative 28. Now we plug in a 1, and I get 2 minus 3, which is what? Negative 1. You stupid idiot. What a teammate you are. I already had the bottom covered, dude. You were supposed to go high so we could win them both. Sorry. Oh, he's playing for both teams. You're right. You're right. I forgot he was also a critical value. My bad, one. All right. So basically, I'm not going to write it all out here, but what's the max? Which of those values is the max? 0 is the maximum value. It occurs at 0. What's the min? Negative 28. Yeah. Now, isn't it kind of crazy that 0 is the maximum value? Is that a good thing? Yeah, sure. Like if you're in debt, you have like no money, you would just love to get back to 0, right? I would love to have a maximum amount of money of 0. Because right now I'm negative money, right? So getting back to 0 is good. Okay, the lunch bell is going to ring, maybe. We'll pick up with example 9 after lunch. Have a splendid, fantastic, awesome lunch, if not better.